This lecture covers the material from the end of Lecture 2 about analog and digital signals. So we finished off last time talking about resolution, quantization error, and dynamic range in digital sampling. Now let's talk about some of the practical considerations that we run into in analog to digital conversion. So first off, simple question, why can't we exactly sample a signal? Well, this would require two things. First, it would require infinitely fast sampling, meaning that the time between consecutive points in the sampled signal would be infinitely small. And second, it would require infinitely fine resolution, so that our sampled signal, like our analog signal, could take on any value in its range. Among other things, this would require infinite computer memory, and so it's not feasible. But thankfully, higher resolution and faster sampling are not always better. So for example, let's consider human body temperature. First off, how quickly could body temperature really change in response to disease? Not really that quickly. And second, what would a resolution finer than about 0.1 degree Fahrenheit really tell us about a disease? Probably not much, and is within the noise of the measurement. What would a resolution less than 0.1 degrees Fahrenheit? So in this application and in most others, we really don't benefit from sampling finer or faster than a certain rate. And earlier we talked about characterizing a signal's range as well as its fastest rate of change, its slew. And so in practice, the range of digitization, should match or be slightly larger than the analog range. Or be slightly larger. Than the analog range. And so for example, let's say that we digitize a 0 to 1 volt range signal, a 0 to 1 volt range using 8 bits, but the signal that we care about, its range, only goes from 0 to 0.1 volts. That is, it's a factor of 10 smaller than the range that we're actually digitizing. In this case, we're going to be wasting some of our digital bits. How many bits are we wasting? Well, if you think about how the 8 bits map into the 0 to 1 volt range, each of the 8 bits, you're going to have essentially 1 to the over 256. The smallest bit is going to represent 1 over 256. The next bit is going to represent 1 over 128, 1 over 64, 1 over 32, 1 over 16, 1 over 8, 1 over 4, and 1/2. Now, which of these bits could actually flip due to changes in the 0 to 0.1 volt signal? Well, 1 over 256 could change. 1 over 128 could change. These are all smaller than 0.1 volts. 1 over 64, 1 over 32 could change. 1 over 16 could change. But 1 over 8 could not change, right? That's a 0.125. That's bigger than the signal will ever be. And so it will never flip. Same with 0.25 and 0.5. So these bits are all wasted. And here's an example from some of my own work that shows a very poor use of dynamic range in a digital system. What I'm showing here on the left is the amplitude in real and imaginary parts of a signal measured by an MR spectrometer, and this big signal right here is actually the RF pulse of the MRI experiment leaking back through into the receiver. But this pulse we actually don't care about. It's not telling us anything useful about what we're actually sampling. It's just leakage that we like to ignore. Yet it actually occupies a much bigger range than the signal, which is actually right here. Right? This is the actual signal that's coming back from the water. If we zoom in on this section right here, If we zoom in on this section right here, this is the blown up of that section, and here we see the NMR signal that we actually care about. And you can see that it's way, way smaller than the RF pulse that's leaking through, which we're spending most of our range on, but we actually don't care about it. This is just a practical limitation that happened in this case, but it would be best to have avoided it. So now we know how to set the range appropriately for a given sampling problem. How about the resolution? How fine should we sample a signal? Well, it turns out that noise is really what limits the usefulness of very, very fine resolution. For example, if the range of noise in a signal is minus 0.1 to 0.1 volts, why should we bother with a resolution of 0.01 volts? That would just be sampling the noise. Those variations we would always just have to attribute to noise. So a good rule of thumb is to say that for appropriate analog to digital conversion, the digital DNR, the dynamic range, should be just greater than the analog SNR. It need not be much greater, or else you're just sampling noise. So now we have our range and our resolution. The final spec for A to D conversion is the sampling frequency. Really, I should say sampling frequency. In practice, the sampling frequency should be greater than twice the highest frequency in the signal. This is the Nyquist condition. In analog signals at frequencies greater than half the sampling frequency, will alias back down to lower frequencies. That is, when we plot the sampled signal, those signals that are at frequencies greater than half the sampling frequency will erroneously appear at lower frequencies. So a very simple example of that, let's say that we have this axis here is time, and that we have samples evenly spaced in time. You can see that if we have a signal, a sinusoid here, that has the same period as the sampling period, we're going to sample it always at the zero crossings, and so it's going to not appear at all, or it will appear at DC, right? If you shift it up a little bit, for example, if we shifted the points a little bit, then we would always get the same value, and it would appear as though it's a constant signal instead of a twice the sampling frequency signal. Often, too, the specs that we use in analog to digital conversion are limited by the hardware that we have available. One good example of this is the story of why it is that we usually have 44.1 kilohertz audio. It seems like kind of a random sampling rate, right? Well, logically what you'd think, what we know is that the human ear can roughly hear frequencies between 10 and 20 kilohertz. So the maximum frequency that we can hope to hear, and thus what we would think would be the best sampling frequency, would be around 40 kilohertz, right? 2 times 20 kilohertz would be 40 kilohertz. You'd think, okay, that's what we'd like to sample at. But 44.1 came about because early digital audio was based on analog video equipment. So early digital audio was based on analog video equipment. Based on analog video equipment. And specifically, the 44.1 kilohertz spec came around because the NTSC video standard, this is like the format of TV signals that used to be broadcast in the US was that you had 245 video lines per field or per image times 60 fields per second. That's the rate at which the image would update, times 3 audio samples per line. If you multiply all that together, you get 44.1 kilohertz. And that's why Sony, back in the day, when they were developing their first compact discs, decided that 44.1 kilohertz was the best frequency to use. And that has stuck around even now in digital audio.